So, so Martin is about to go off with a bang, if I might use the pun. So let's just hear him, and then if you have any questions, usually you take questions during the talk, right? Okay.
Yes. Thank you. So as Thiago said, are there questions from yesterday's talk? Well, we can have questions from yesterday's talk, not from today. Yeah, no? Okay. So the plan for today is to complete what we started yesterday. So to get this worked example on the expansion of the universe, connect to some subparameters of the model with observables, introduce dark energy, and then we'll go on to say some things about the thermal history of the universe and the cosmic microwave background. And if we have time, we'll say something about the large-scale structure to finally connect with Darren Croton's lectures. So we stopped yesterday here, right? A bit beyond, but so we got to this Friedmann equation. So just to recall, this A parameter we call the expansion factor of the universe. So it tells us how the scale factor of the universe, and it tells us how all scales change when the universe expands in a homogeneous universe, of course. For now, we are only looking at the mean of the universe, and we already learned that the universe is way less concentrated than what we see in light. So we see a lot of galaxies, but in reality, most of the mass is dark matter. Dark matter is more smoothly distributed, yet there are large fluctuations of dark matter, and we are looking at the mean of all this, right? And the second half or the last third of the talk will be devoted to perturbations. But in this homogeneous universe that's expanding, all distances scale as A. So A is the scale factor. If A doubles, all distances double, right? And we derive this Friedmann equation by using the homogeneity, by using Gauss' law, and by just thinking Newtonianly. So we have we considered a volume element, and with respect to some arbitrary center, right? This was, of course, an analogy because we really have to do things with general relativity, and I'll give a little glimpse of that. But still, these analogies are also good to have some intuition, right? Because if you have some self-gravitating fluid, and you have this volume element, it is expanding. What produces the gravitational field is the mass inside the sphere. So we think it's like you take a lot of stones and just throw them. You know, by the effect of gravity. If the velocity is not enough, the stones will go back. If the velocity is higher, they will go on forever, right? So these are the three solutions I have shown at the beginning of this equation. So this gives us some intuition. You know, the universe may expand forever, may recollapse. Of course, when we put things different from stones, so things different from dust, when we put some equation of state, the behavior may be very different. Here is the total mass that matters, of course, for gravity. And this mass here is composed of many things. We learned yesterday about dark matter. Of course, we know there are baryons. We know there are photons. And there is maybe also dark energy. So this is the sum of everything. And as we saw yesterday, the evolution of this with respect to A is given by some conservation equation. And different components will scale in a different way. And if the universe has curvature, we have this term also here that appeared already. If we have a cosmological constant, we can write as an equation of state P equal minus rho, and that gives you, by energy conservation, that it is constant. Or it may arise naturally from the Einstein equation. So sometimes we include here dark energy, including cosmological constant. Sometimes we put it outside. So here's when we put a cosmological constant explicitly. So we introduced the density parameters, which we are normalizing by the density parameters that makes this sum being h naught over 8 pj over 3. So with this natural scale that appears, the critical density that makes the universe flat, so k equals 0. This is the critical density. If we know the Hubble parameter today, we know what it is. But we use these non-dimensional quantities, which are way more convenient to use. You can do something in analogy with K, right? So you divide this equation by H naught. So here's the critical density to the minus 1. And here will be something that scales to the A to the minus third. And we call this something A omega K. And the same for lambda. So we divide this by everything by H naught. This lambda over h naught, we call this omega lambda, right? And finally, we can rewrite this equation in this very simple form. So as we'll see, h is the expansion rate of the universe, right? It's the fractional variation in time of the scale factor. And it is given by this very, very simple expression where you have all these adimensional quantities and the scaling with A. Any questions so far? Okay, so this was yesterday's talk, right? So let's go to today's talk. We'll talk a little bit about the geometry. Last talk was only about the dynamics. Now will be the geometry. And I like a lot this quote by Hermann Minkowski. As you know, Hermann Minkowski is this mathematician that helped Einstein to put his equation in a very beautiful and a very geometrical way, right? So Einstein was very intuitive. He's not joking, he's not a mathematician. He writes the equations in a way that they are sort of ugly. And Minkowski puts, you know, okay, this is four-dimensional space-time. If you think in 4D, you have everything has a geometrical meaning. So you have quantities like vectors that don't change when you make rotations. You have something like vectors that don't change when you make translations, when you make boosts, right? So four-dimensional quantities are the natural quantities to think when you think in special relativity. So people think he's a really mathematician, you know, fourth dimension, space-time. And this quote is really great because he says, the visions of space and time that I will present here originate from experimental physics. And that's why it is so powerful. So we have never to forget that we are doing physics. So what motivates us is the universe, is our observations of nature. And we find elegant mathematical ways and never the way around. I already heard like physicists saying, oh, this is so elegant, it must be true. No, that's a very false statement. Okay, so coming back to the geometry, to understand the full picture, we really have to understand the geometry of the universe. We have to look a little bit in the Einstein equations. Of course, it is not a general relativity course. I'm not making any calculation, but just give a hint, some ideas, some concepts that we need to understand the problem, right? So, okay, so as you know, distances in general relativity are given by a metric. This is not strange to us, right? If you write the standard Euclidean equations, but you work, for example, with polar coordinates, things change, right? For example, everyone knows these line elements. If you want to make a distance between 2 points in polar coordinates, you have to use this, right, in 3D polar coordinates. So this is normal, right? Here, we are not only working in, so if I want to know some distance element in spherical coordinates, I just write dr square in one direction, you know, a differential element in polar coordinates. I just write dr square, and I use this expression, and okay, we get the little distance in polar coordinates. The only difference when there is curvature is that you have two quantities here that now depend on r. So these are the measurement of the deviation from Euclidean geometry. But the expression is very familiar. And we have a lot of freedom to change coordinates in general relativity. So you choose the radial coordinate such that the area will just be given by this radial coordinate here. So when I want to measure an area, I fix this dr. Oops, I fix dr. I just want to measure some area element on the sphere. So the dr is 0, right? And I choose this distance such that the area will be 4 pi r squared, like in normal Euclidean geometry. It's a choose of coordinates, right? So I make this choice. I call this r prime, but then I get just rid of it. So I can write this as 1 here. And I have only one function that's left. And it turns out, when you use differential geometry, that if the curvature is constant, the expression is this one here, okay? So the final expression for a spatial section, so the three-dimensional section of the universe, with a constant curvature is like this. As I said, we are very familiar with this part, and this is what appears new due to the curvature of space. But again, I chose this coordinate, this specific choice, such that r gives us the area. The area of the sphere, regardless of any curvature, will be given by 4 pi r squared. There are other choices of the metric that people use, but this one would be convenient. Any questions so far? Okay. Okay, this is just how we relate the coordinate measurements with something that it's a physical meaning. But this is only on 3D. This is only the space part. But let's look at the geometry. In the Euclidean geometry, of course, the internal sum of the sum of the internal angles of a triangle is 180 degrees, right? When you have a geometry which has negative curvature, the two straight lines will look like something like this. If I make a triangle here, the sum of the internal angles is less than 180. And if you have a positive curvature, the internal sum is more than 180. So if you can measure curvature, you don't need to have an extra dimension to be looking at something. If I'm in a curved space and I draw a radius, and then I go around this radius and draw a circle, in a flat space-time, this will be for 2 pi r, right? If I'm in a universe which has a positive curvature, it will be more. The circle will be less than 2 pi r. And if I'm in a hyperbolic universe, the circle will be more than 2 pi r, right? So this is an analogy just to have a picture. If I could see a 2D universe in 3D dimensions, I would see a spherical universe is like this, a hyperbolic like this, like a saddle, and the flat is like this. But as I said again, there's no need to be seeing this in extra dimensions. You can just measure angles and any geometric properties within your surface, and you'll be able to measure deviations from the flat, right? This is very familiar, this is familiar, this is, well, so you can fold in this many times, and this will look like this. So it sounds more familiar, I don't know. Any questions so far? Okay, so this is only the space-time, the space geometry of a homogeneous universe. You only have these 3 choices. There's no other choice. Either it's flat, spherical, or hyperbolic. And some people like to call this flat, open, flat, closed, and open. Is a misnomer because, okay, this is closed, but you can construct a closed universe with a flat geometry by topology. You can construct a closed universe with hyperbolic topology. So it's not a good nomenclature. It's really spherical, hyperbolic, and flat. We can discuss this. There are questions. Okay, I spoke about special relativity, which I'm sure you all are familiar. And we, in special relativity, you know, what matters is what's the invariant under boosts, under transformations, is this combination here, right? Time square minus the distance square. So we need to build this structure for the homogeneous space-time. And we already know a bit of this part because it's the 3-dimensional part. The time will be very easy because we can choose a time in a homogeneous and isotropic universe such that this is only dt. Nothing changes here. It's just dt squared. The difference is that we work in coordinates that are not expanding with the universe, right? We wrote this little r in the whiteboard yesterday. So our coordinates are fixed. The universe expands. It's just a choice of coordinates. So to have the physical distance, we have to multiply here by a, by the scale factor. So as all the scales expand with a, this is the final form of our metric. Okay, this is the space, only the space component of our metric, just multiplying a squared by what we derived before, and the full space-time is this, right? Okay, so this is how we connect time coordinates and space coordinates with something that's invariant, and this is really important. For example, when we say that light propagates in new geodesics, it means that light's propagating in things, in combinations of coordinates, they make this d squared equals 0. So if you want to study the propagation of light of photons, it's here. It's really simple, right? And this is known as the Friedman metric. So we will use this to study the propagation of light, and as all information we get in the universe is from the light, we will learn a lot from looking at this thing. Are there other questions up to now? Okay, so let's think about light rays. This is time. We are here in a given time, t0. This is the space surface. And we receive a light ray that was emitted in a t1 in the past. So t1 is smaller than t0. So a light that was emitted in the past, it propagates through the light cone, of course, with the velocity of light, and it reaches us. We choose our center as our position as the center of coordinates, right? So we look at the light emitted, let's say, by a distant galaxies at a position r1. arriving to us at position r0. It was emitted at time t1, and it arrives at time t0. So if we look back to this metric that we showed here, and I said, look, this light propagates when this is 0, right? And also, as we are in the center of the coordinate system, this light is propagating only in the right radial direction by definition, right? So light is getting here. We are in the center of the coordinates. So d theta and d phi are 0, and light propagates in something that makes this equal 0. So it's like this, right? This is the connection between time and radial distance in the universe for the light propagating. So I can already write for this position, if I want to know, you will see that this quantity is very relevant because it's connected to the expansion rate of the universe. So if I want to compute this quantity, so the integral of dt over a is just a spatial difference, spatial integral, right? And we, of course, we can integrate this thing. There is an analytic expression. It's a sinus or hyperbolic sinus. So what does it tell us? We are at a fixed coordinate 0. A galaxy is at fixed coordinate r1. When the universe expands, still r1 is fixed if it's expanding with the bulk of the universe. So this thing changes because time changes, but this thing will not change. So we can think about two light rays, or better, we can think that we have a wave, which is light, is a wave, and we'll think of these two crests. We'll think of one crest emitted at time t1, and the second crest emitted at time t1 plus delta t. And we'll receive this thing at t0 here, and this thing at t1 here, right? t0 plus delta t0, right? And what's important is that this delta t0, what's the difference between the two crests, it exactly gives us the wavelengths or the frequency we can compute with this delta t. So we know the frequency of the emitted light, and we can compute with what I will show now, the frequency of the received light, right? And this is, of course, connected to the redshift. So we'll make a connection between something observable, which is the redshift, with something of the model, which is this scale factor. So let's go. We take the first light ray emitted at T1, a second light ray emitted at T1 plus delta T1. The position doesn't change. We receive them at T0 and delta T0. And as I said, this integral in time is a function of space. So it doesn't change for the two light rays, the one emitted first and the one emitted second. So we have this equality here, right? So we can rearrange a little bit the things. And of course, this interval is infinitesimal compared to the time, right? It's really, really infinitesimal. I mean, we are speaking about the frequency of light compared with, cosmological times. So we can, of course, these integrals become just a product. And you have this relation, right? So the ratio of the two time intervals is given by the ratio of the scale factor in these two times, right? But the ratio of these the ratio of these two time intervals is exactly the ratio of the wavelength, right? Because the wavelength just c delta t. So the ratio of wavelength is exactly the ratio of the scale factor. So if we compute the redshift, it's given by this ratio. The scale factor today over the scale factor when light was emitted minus 1. I mean, these calculations are absolutely trivial, but we are finding something really deep here. We had a model, okay, we skipped the general relativity part, but it's really simple. It's a model of a homogeneous and isotropic universe. It has one function of time, which is A, and we can directly connect this function of time with a redshift. That's something that we measure of a galaxy, right? So it's something really deep. And we can have also the choice of any, we can choose any normalization factor for A. We can multiply by any value. So we usually choose A at t of 0 equal 1. So we choose by construction, just to simplify calculations, that the scale factor is normalized to 1 today. So if we do this, we have this relation between the scale factor and the redshift, right? So we can go in the previous equations that I have shown that show the Hubble factor as a function of density parameters, right? The omegas and powers of A. I can now write this as powers of Z. Any questions so far? Okay. Okay, it's constant in space, right? So given, given the position of the observer and the emitter here, right? We choose these coordinates to be co-moving. So when space expands, if the object is expanding with the universe, it will not change its coordinates, just by construction. And this allows us to write the metric like that. You may say, well, what if I didn't make this choice? Okay, you can make a choice that expanding, and it will not change, but you can normalize, so you get the same results, of course, regardless of your choice of coordinates. But our choice was to make things simple, right? Any other question? So for those that have seen this before, okay, but for those that are seeing this for the first time, I hope you really get excited because, you know, we are beginning to connect very basic questions, very basic things, but connecting a model to the data, which is exactly the title of this set of talks, right? Okay. Any other question? Okay, now let's make a second connection, and this is connected to distances. As you know, also in general relativity, because you have this freedom of choosing choosing coordinates, there's not one single definition of distance. That's not a problem. If you define some distance that you can measure, and you replicate theoretically the way you measure, you will define a distance, right? And that's fine. So as long as you are consistent with your definition, you have expressions for distances. You may have 10 definitions of distance, but they are connected to 10 ways of measuring the distance. If you use the right definition with the right measurement, no problem at all, right? So one very often used way of measuring distances is by the light. We gave this example yesterday, that you have cepheids as standard candles. So if I know the flux of intrinsic luminosity of some quantity, and I measure the flux here, I just use this inverse square law, and I can measure the distance. So we define in cosmology a distance that is really given by this, by what I just said. You take the luminosity of something that, let's presume that I know the absolute luminosity. You divide by the flux, which is measured, right? So this is total energy per unit time. This is energy per unit time and area. So I divide L by 4 pi f. And this is by construction, something that I call luminosity distance, right? Any question? Okay, so this is a definition. But now I can work out this definition using the things we learned and see an expression for this in terms of the model, right? So first, I need to know the area because I will divide. What I will do is I have an object emitting light. I know the luminosity, and I want to compute theoretically what I would get here as a flux, right? So I know the luminosity, and I want to see what I detect as a flux. And I will write this theoretically, and then I'll build up this expression here. So to know my total area, what I do is to use that metric. But if you recall, the metric, the R, was chosen such that the expression for the area is the normal Euclidean expression. So the area is just 4 pi r squared. Of course, to get the physical distance, I multiply by the scale factor. So the area is just given by 4 pi I squared computed now as times R1 squared. But there is an effect, right? The light traveling its cosmological distances, it will be redshifted. So the energy of the photon will change. So one thing is the total luminosity emitted, but the flux I will get is not just weighted by the area, but is also weighted by the loss in energy of the photon, right? And now I know the ratio of these frequencies because I know the ratio of the wavelengths, and I know that they are proportional to the ratio of the scale factor, which is given by 1 plus z to the minus 1. So I know that the photon emitted with frequency nu1 will arrive us at frequency nu0, and this loss of energy is given by 1 plus z to the minus 1. But not only the photon will lose energy as it propagates to us, time also changes. And recall that luminosity is per unit time, and the flux is per unit time. So the unit time changes for us, and we already worked out how it changes. The time changes by the ratio of the scale factors, which again is 1 plus z, right? So when I plug all these things, okay, so this is, the flux here is integrating all the photons I get in some sphere. The sphere, I know the area, right? But the total energy that I will get, this L prime, is not really the energy emitted, but I have to weight this by the energy loss of the photon and by the variation in time. So when I do this scaling here, I get this expression here, right? So if I take the definition of the luminosity distance and I plug in the information I have from the cosmology, I have sorry, I'm not using this definition yet. I'm just computing the flux, assuming that I know the emitted luminosity, which is L. So I know L. I want to compute the flux. I'm not looking at this. I'm just computing the flux knowing L. And to compute the flux knowing L, I know that I have to divide by the area and also by these losses of energy. So now I have a relation from the model connecting the total luminosity with the flux in the detector. Now that I have this expression, I can plug into this definition and, well, you see that the expression will be really simple, right? So plugging in the relation between the total luminosity and the flux detected, I have, and plugging into the definition of the luminosity distance, I have an expression for the luminosity distance, which is 1 plus E squared times the scale factor today times R1. Any questions so far? But who's R1? I mean, how can we know R1? Well, we know that the integral of R1, that integral in space, is connected to an integral in time. You remember, because of the light propagation? So let's just recall this. Oops. Okay, I don't know who is... No. You can use this time to make questions. So I don't know who is R, but I know that some function of R, which I can invert, is given by some integral in time, and this is the scale factor, right? So I don't know who is R1, but I know how to get it. And if I look again at the luminosity distance expression, okay, I don't know, but I know how to get it. I know how to write it as an integral of the scale factor. And okay, that's it. Any questions so far? If we look at that integral that I just shown, recall this. If I had that integral, sorry, there's a square missing here. No, it's okay, sorry. The square, oh my goodness. Animations make you go slow. Okay, so this is all square, so I take the square, and the luminosity distance is just the product of all these things, not squared, like here, right? And I can write that integral of 1 minus k r squared, just compute this integral, right? And you find this expression. I mean, they're not very pretty, but of course they're really simple. And here is r. So if I want to get r as a function of this integral, I just invert this function here, right? And this k, exactly the curvature that appeared before. How about this integral? Well, if we tweak a little bit the a, and we recall that a dot over a is h, you can show that this integral is just the integral of 1 over the scale factor. And now I can write the scale factor as a function of redshift. This is a function of redshift. So all this is an integral as a function of redshift, and it depends on the cosmological parameters that I've introduced earlier. So I can write R1 as a function of cosmological parameters, and once I do that, I have a luminosity distance. So the expression is, I mean, it's fantastic. You know, we are discussing the universe as a whole. We have a model. As you'll see, this model works well, and we can write in one single line a connection between a luminosity distance that, if I have a standard candle, I can measure directly, and an integral of parameters of my model, which are cosmological expansion rate and all these omegas depending on all these components. So I have a connection of the model quantities that appear here, a redshift that you measure, Z, you measure directly, and a luminosity distance that I will assume that we can measure using standard candles. Any questions so far? So let's take a case, very simple case, with k equals 0. So this integral is just r. This thing vanished, so the expression is simple. So the flat case, a lot of people deal with the flat case because the curvature of the universe is really small. So this is the expression of the luminosity distance. We recall the first slide of today's talk, which is here. So we can plug all this, and again, in a single line, we can write very explicitly the dependence of the luminosity distance with the parameters of the model and the expansion rate of the universe. Any question? Of course, I'm going really fast, and I presume that you can download the slides and make the calculations, and there are even a list of exercises if people want. So we can make now, this expression is an integral, to have an idea of how it goes. For low redshift objects, we can make this expansion, right? For low redshifts, this will be proportional to Z. This is 1 plus z. So to first order in z, if you make an expansion, you get just here, right? The luminosity distance is h naught times 1 plus z. But 1 plus z is just the velocity, right? It's cz for small velocities. So you get really Hubble law at first order. Okay, so fine. We recover Hubble law. This is observed. We are good. So now let's go to second order. And it happens that the expression is like this. You can, again, make the calculation yourself very easily. And this is a parameter that tells you the deviation from the linear Hubble law relation, right? And this deviation, which was called minus q naught, is called the deceleration parameter. So if the universe is accelerating, the q naught is negative. But as everyone knew that the universe was decelerating, they put a minus here. So a decelerating universe is a positive q, and people wanted to know how much the universe decelerates. Because if it decelerates a lot, it will recollapse. And if it doesn't decelerate so much, it may expand forever. So that was the quest. The quest, less than 20 years ago, was trying to determine how much the universe decelerates. And the expression for this q, of course, I say is connected to acceleration. It's here, right? It's the second derivative, so really acceleration. And you put this minus because you expect deceleration, so you expect this to be negative. Q would be positive. Again, there are exercises that you can work out, very simple, to have the expression of A2 naught of Q0 as a function of the quantities of the model, I mean the densities, the density and the pressure, right? And you can also derive this equation to third order, to fourth order, and if you do to fourth order, that will be connected to the slide I showed yesterday with the linear Hubble law relation. So if you take the higher order elements and you rewrite, you can linearize this equation even for high redshifts. That was a recent result that I measured, as I mentioned yesterday, with a 2% deviation on the Hubble law. But okay, let's keep second order. Okay, now we'll see how this is connected. We learned about dark matter yesterday. We'll see how this is connected to dark energy. And well, we all know this. Okay, so type 1a supernovae, everyone heard about that. What is the advantage of using type 1a supernovae? They're really, really luminous. When a supernova explodes, it shines as much light as the whole galaxy. So you can know the 10 to the 9, 10 to the 10 solar luminosities. So you can detect these objects really far away, really at high redshift. And you're interested in seeing and looking at high redshifts. Why? Because you want to see the deviation with respect to the Hubble law. So the deviation with respect to linearity. So you want to go to high Z. So it's useful to look at these deviations. Also, they are very homogeneous. So if you look at the light curve, so for example, magnitude is a function of time. You see that all type 1a supernovas, they have very, very similar light curves. And they have an absolute magnitude, which is very similar. If you scale this by a single parameter, you can put all these very different supernova in the same curve. So if you can calibrate with nearby supernovas in galaxies where you have Cepheids, for example, then you can use the same thing for high redshift supernovas, right? Of course, there's issues whether they are evolution or not, and as I said in this course, we are avoiding all these discussions because of lack of time, but all this has been very thoroughly studied in the literature, and we can give the references. But the point is that supernova can be made standard candles, as the Cepheids were made also standard candles. And with this, you can measure what? Exactly the luminosity distance, right? That's why we did all this thing. If you have something that you know the absolute luminosity, and luminosity distance is exactly the meaning of this, you can compute the luminosity distance. The problem is that there is one supernova each 500 years per galaxy, right? So it's not a very nice subject for a graduate student to put this person looking at the galaxy for a long time. The likelihood to complete in the thesis is very low, unless you have many, many students. But what you can do, instead of look at a single galaxy, look at many galaxies at the same time, and just subtract the difference. So of course this was enabled once you had digital images, digital image processing, good image quality, and many factors. So that happens that this was possible to find many supernova at the end of the 20th century, right? So the program was, I look at pieces of the sky, with a cadence of a week, for example, and if something appears, it can be a variable star, it can be a nova, it can be many things. It can be supernova, it can be type 1a supernova. If you know it's a type 1a supernova, you are in the business, you can compute the light curve, and you have absolute magnitude. So this is what was done by these two teams, the High Z Supernova team and the Supernova Cosmology Project. They use data from very different instruments. But here's what you see, for example, these are galaxies, and you don't see anything, but when you compute the difference in a very careful way, something appeared in the galaxy, and that's a supernova. So when these people did this at the end of the 20th century, and they made a plot like this, so it's exactly a Hubble plot, and I showed you that the linear part is just the Hubble relation, and then you should expect this to bend downwards if the universe is decelerating as expected. But what they saw is the contrary, that this thing was bended upwards. So the universe was accelerated. And the first papers, they understood this very well. They thought that like maybe omega is 0, maybe just, you know, it's not decelerating, but there's very low mass, until they had no solution, then adding some new component that will make the universe accelerate. And they use a cosmological constant because this was the simplest thing. So the expansion is accelerating if you believe in all this, but we can discuss in the questions. This is not the only observer, but it was just the strongest that made a big impact. And the deceleration, as requested by the exercise, you can show it's just given by this expression. So to have negative to have a positive acceleration, you need to have a negative rho plus 3p, right? We said yesterday that normal matter, like galaxies or dark matter, just have this pressure negligible, right? For light, the P is 1/3 of rho, so it doesn't help, it's positive. So for all the things we know, the pressure is positive. And recall that this is P over C squared. So it's, I mean, even if there is like a fluid that it has a negative pressure, like a elastic thing, you know, it won't solve. You need to have a relativistic pressure that's negative. And this is, if you add the cosmological constant, this is very natural. The cosmological constant gives you a positive thing, or you need to have something exotic, very exotic, so that this sum is negative. And we call this dark energy. So either a cosmological constant or something more exotic, such that this is negative. Any questions so far? Okay, this had so what fits the data already at that time was that you need a cosmological constant normalized by these omegas that I have shown before of 0.7 and an omega matter of 0.3, which is very close to what you find when you look at galaxy clusters, as we saw yesterday. So this is sort of expected by local measurements of the dark matter, and this is the new thing that's needed to make the universe accelerate. And this thing had such a high impact that this discovery was awarded a Nobel Prize, right? Any question? Okay, but there are many other evidences for an accelerating universe. One of them is the age of the universe. We saw this plot before. If the universe has positive curvature, it will recollapse. If it's zero curvature, it will expand forever. And if it has negative curvature also. But always the curvature is in this direction, right? So all curves have, they are convex, right? This means that if I take here, the derivative, so if I take the derivative of the scale factor with respect to time, h naught, a dot, and I take a dot over a, it's very easy to show that the inverse of a dot over a, so the inverse of the the inverse of the Hubble parameter will give you the extrapolation, the linear extrapolation of this derivative here, right? So if very simple, if you are here and you have h naught, the inverse of h naught gives you the projection here. So this is the age of the universe, right? So these three curves, the here, here, and here, are the three possible solutions when you have only dust, when you have only dark matter, for example, no cosmological constant, no dark energy. And they all are banded in that way. They are convex. And if I compute the age of the universe just by h naught to the -1, I'm always estimating the real age of the universe. So h naught is a lower limit to the age of the universe. But when you use the values of h naught and you compute it, these values were sometimes lower than the age of the oldest stars. How come the universe can be younger than its content, right? So that was known as the age problem. Okay. Now, if the universe changes concavity, so if there is an acceleration, then there is this concavity here that it can become concave, then it's the opposite. Then h naught, which is the linear extrapolation, is a lower limit to the real age of the universe, would be here in this yellow line. So accelerating universe also solves the problem of the age of the universe, which maybe you young people never heard about this problem, but it was a long-standing problem of cosmology. Okay. So many people may say, well, but you see these things accelerating. Why? Because you look at supernova, and supernova is dimmer than you expect because of the accelerated expansion. But other things may make the supernova dimmer. For example, if there is dust, if there is evolution, if there is any systematic thing going on with redshift, the universe will appear to be accelerating, but it's just a systematic effect. Recall that I told you that systematic effects are very important, right? How can I test this? You remember the plot I had shown yesterday where you have the different components. So now, if a component is constant, it dominates the energy density. But when I go to the past, what happens? Dark matter dominates, and then radiation dominates, right? So the only time where I see acceleration is in recent times, where the cosmological constant would be dominated. But when I go backwards in time, I would be looking at the universe from the theoretical side. I would be looking at the universe that is decelerating, right? So acceleration is something more or less recent in the history of the universe. So it's easy. If I look at this deceleration, acceleration, if I see the acceleration increasing with time, then it's a systematic thing that accumulates. But if I see the acceleration happening in some time and then going off, a systematic effect cannot account for this. I mean, it has to be tweaked to do this. But the model accounts this very easily, because you expect that in the past the universe was not accelerating because it was dominated not by dark energy but by dark matter. And that's what they saw when they started looking at very higher redshift galaxies with Hubble Space Telescope. You start seeing a deceleration, right? So this is the curve, the dashed line predicted by the model, right? And if you expect like constant acceleration, you'll get this. So we are really seeing the deceleration. And these are results from last year, where you combine, that's a very complicated combined data sets. That's all this discussion about systematics, but they did a very good job. So they combine all these large supernova data sets down to the Hubble ones, and down to high redshift, higher than redshift 1, and you get this very, very well-defined curve, and it's well fitted by omega matter 0.3. There is also an important thing that supernova, they can measure acceleration, but they can measure omega lambda, and this is consistent with the universe being flat, so that's why they report only omega m. But you cannot measure the variations in the ratio P over rho, right? P over rho, remembering that in cosmological constant is -1. But if you combine with other data set, for example, with CMB that I'll mention later, you have this W that's really close to -1. It's incredibly close to -1. That's why Thiago asked the question, when we'll get fed up about dark energy and just believe it's lambda. Everything points very close to cosmological constants, right? Any question up to now? Okay. So, the supernovae provide a strong evidence for acceleration, and a very simple way to accommodate this is through either a cosmological constant or dark energy. And people didn't like the cosmological constant because this is connected to vacuum energy, but in particle physics, the vacuum energy is really huge. It's 122 orders of magnitude higher than what you measure. So the particle physicists were comfortable saying, well, there may be some phenomenon that makes the vacuum energy 0. This they were okay with being 0. But being a tiny value compared to theory, they don't like. So a lot of people don't like cosmological constants because there are lots of issues with theory, but so you can put this like a dynamical term, another component of the energy density that they call dark energy. In any case, 2/3 of the omegas that I have shown, is in the form of dark energy or lambda. So accelerated expansion is one evidence. The age of the universe is another evidence. I'll mention soon about the curvature, but remember that omega k is 1 minus the sum of all omegas. In other words, the k is 0 if the omegas of all components are 1. Okay? So if I measure that the universe has 0 curvature in a geometrical way, and I find that omega matter is 0.3, I need 0.3 plus something to be 1. So a small curvature of the universe is also an indirect indication that we need to have something else to make the curvature flat. I will also mention about the integrated Hausdorff effect later. And in any combination of cosmological observables, you find that you need something to provide this acceleration, something to provide this mass component to make the universe almost flat. So this is what we call cosmic concordance. Many different observables constrain many different combinations of parameters, but when you combine all these combinations or any two independently, you always get evidence for a dark energy. Now, as I said, people, if you don't like lambda, there's a whole universe of possible models, cosmological constant, scalar field with many different initial conditions, with many different Lagrangians. You have quintessence, that's a model we proposed. We tried to unify dark matter and dark energy. We tested many models, we compared to observables, and basically we rule out this unification. So dark matter and dark energy cannot be made of the single thing. That was nice. I mean, I think we all like the Occam-Razor argument that we want to have the simplest explanation of things. Some theoreticians, they get very happy when they generalize things. They add new degrees of freedom. But in truth, we only have to generalize if nature requires us to do this to accommodate the facts. Otherwise, we don't want to generalize anything. We want to keep it very simple, very special case, the list of assumptions that explain things. So we tried to get rid of an unknown component, have a single one, but it didn't work. You have different, well, many things. It's meleca in Portuguese, because meleca has this attractive thing, so it's like a negative pressure, but it doesn't work either. So there are many, it's, hundreds literally models for this thing. And another possibility is to modify the general relativity. And again, there are many models, f of r, Hondesky, beyond Hondesky, Horava-Lifshitz. They are leaking from extra dimensions and all kinds you can imagine. So there's a lot of things going on here. Of course, I want to mention any of those. Any questions so far? Okay, so finally I did go fast, so that's no question. But are there any questions? Not really? Okay. This is manipulation, right? So, okay, so we completed this pie chart, the cosmic pie, and now we are ready to go to a second topic, which is the thermal history of the universe. So let's see, all the observations we discussed were using galaxies so far, right? The expansion of the universe, the acceleration of the universe, the age of the universe, so old stars in galaxies. So it's like a local and very recent universe. But as the universe is expanding, of course, we can go backwards in time. As you know, when we compress, if you go backwards, we compress, the universe heats. And we saw that the temperature in radiation, for example, goes with the inverse of the scale factor. So if I go to the scale factor, a billionth of what it was, what is it today, we'll have a temperature that's 1 billion times the current temperature of the universe. So a lot of things will happen because of these high temperatures. So the furthest I go past in the history of the universe, the higher the temperature. So I will start at a given point where we know very well the physics, because it's nuclear physics. So my t equals 0 will be a second after the Big Bang. Remember, the Big Bang for me is just an extrapolation of the curve we measured today. So just call this t equals 0. So very early after this very hot and dense period of the universe, of course, when the temperature is very high, you have no molecules, you have no atoms, you don't have even nuclei, because the kinetic energy is so high that there are collisions and so on. So at some point, you don't have even nuclei. You have only the partons, only quarks and gluons, and before that, other things. But let's start our story at the moment where you already have the nuclei and the nucleons, right? So it's, we call this, well, these hadrons, right? So we're at a point where there are hadrons already, and the universe cools down. As the universe cools down, nuclear force may make these two hadrons get together, and they, of course, they are colliding a lot, so there is a probability of these encounters. When they get close, you can get a bound object, and you form, for example, deuterium. You can form tritium, you can form helium. So this process is called nucleosynthesis. It's the first moment in the history of the universe where you start building nuclei, right? And of course, you start producing simpler nuclei, and then you go higher and higher. But there is a competition. On the one hand, there is the interaction rate willing to form the bound nuclei, and on the other hand, the universe is expanding. So as the universe expands, the probability of these encounters get less and less, just because, you know, temperature is decreasing, the distances are growing, and so on. So you have a competition between the rate of producing new elements and the expansion rate. So what happens is that this production stops at a given point and stops at the lithium, right? So you produce a lot of elements, but you only produce at most lithium, beryllium. These are the heaviest things you produce. So you start only with protons and neutrons. As time goes, you produce neutron, of course, alone that is left, it decays. But you produce hydrogen, you produce helium-4, and all isotopes of these things, and lithium and beryllium. So if you are able to find the primordial abundance today of these nuclei, you can constrain what was happening in this very early time of the universe. And you know very well the expansion factor at that time, because you know it's radiation. We worked out this yesterday, is 1/2T, period. So if you look at these quantities, theoretically, at the observed quantities of helium, deuterium, lithium, they depend on the density of baryons, of course. That's only what matters. The expansion rate of the universe and the density of baryons. It's only 2 parameters, but the expansion rate you know, because the universe was dominated by radiation. So basically, you can move this quantity that I don't know, the baryon fraction, and you will produce different quantities. Once you observe them, once I observe them, and these black boxes represent the observations, if I find a given value here, it's the value of the baryon density that produces these abundances. So the only fact that let's say to a first order approximation, the only fact that these quantities, the observed abundances, they can all be explained by a single baryon density already tells you that this picture makes a lot of sense. Of course, when you go to precision, there are differences, and that's a whole thing, but let's look at the big picture, right? So the production of all these elements can be done with a single baryon density, and we like to parameterize this as a function of number of photons per number of baryons. So this is eta, the eta parameter here, right? So we can measure the quantity of baryons, and deuterium, as it's not produced by stellar evolution, as far as I know, is the best barometer because you're supposed to be detecting the primordial abundances of this quantity. So anyway, when you look at this, when you measure the baryon density, is 0.04 by nucleosynthesis. But you just said the omega matter is 0.3. Yes, but this thing that I measure here is all the density that participates with the strong interactions, is what participates in the nucleosynthesis. So it doesn't include dark matter, but it's sort of consistent with the abundance of baryonic matter, with normal matter that you measure in the local universe, right? So you have a direct measurement of the difference between the baryonic and the dark matter. And of course, all this calculation is independent of the presence of dark matter. The universe is dominated by radiation at that time. So I really measure omega baryon. Okay, then the universe cools down more, and when it gets below some given energy, the plasma, so the electrons and these nuclei that were free, you begin to have nuclear neutral matter, and in neutral matter, the light starts propagating. So here, you know, light is interacting a lot with the electrons, electron with the nuclei. So it's a coupled photon baryon fluid. There is some curiosity that if I ask naively at which temperature this happens, you say, well, it will be the ionization temperature of the hydrogen, right? When I'm above the ionization temperature of the hydrogen, this is all plasma. When I'm below, the hydrogen gets its electron, but not. It doesn't have it doesn't happen at 13 eV. It happens at 0.26 eV. But how come? I mean, how can you keep the universe ionized with such a low temperature? Because you know the distribution of velocities is a Gaussian distribution, right? So the peak is at some point, but you have this tail. But the point is that for each baryon, there are 10 to the 9 photons, okay? So if you look at the Planckian, this thing on the tail, there's still many photons with high energy as compared to the number of atoms there, because there's 10 to the 9 photons for each baryon, right? So this tail keeps the universe ionized for more time than what you would expect. And this transition happens not at 13 keV, but it happens at 0.26, which corresponds more or less to 3,000 Kelvin, right? You always keep in mind that 1 electron volt is equivalent to 11,000 Kelvin. And so this happens because this ratio, baryons over photons, is really a small ratio. Okay, so this is really a bilingual talk. Now we have lots of things in Portuguese, but we call this recombination. So when the universe cools down and ceases to be plasma, light propagates. So this is this transition. So when we are here in our galaxy and we look further in time, of course we are looking in the light cone, we see things older and older and older. So there will be some point, some distance, which I see this transition between a universe that was a plasma and a universe where this light can propagate, right? So I should be getting, at a higher enough redshift, this light. Well, there is Ober paradox why I don't see this light. Well, we don't see in the optical, of course, because there is a redshift. And the redshift of this thing is about 1,000. So something that would be at 3K Kelvin, so 3,000 Kelvin, is redshifted by a factor of 1,000, and we see at a 0.3, well, and we see it at 3 Kelvin, right? So this radiation is getting to us, but just redshifted. And for the older guys, when we had this TV and we could tune in between where there was no channel, we had this noise, like about a third of this noise was produced by this radiation, which we call the cosmic microwave background. So it's a black body because it's just thermal. It's just a thermal thing that is here. And when it decouples, we should see a black body radiation. So this is a measurement by the COBE satellite of this black body spectrum. And all this so as a function of wavelength and the intensity of the radio waves, each of these error bars is multiplied by 100 so that you can see. So it's the best black body ever. And this is the temperature of the black body. So just measuring the density of photons can give us a measure of the omega parameter associated to photons today, right? As we have omega matter, omega lambda, omega baryons, we have omega gamma, and today is really small, of course. It decreases with 8 to the 4th power, right? Whereas the matter decreases with 8 to the 3rd power. So, to the -3, of course. So this is really small today. What you see, well, of course this was a huge impact. The discovery of the CMB gave the Nobel Prize for those that discovered, Penzias and Wilson. And there was this COBE satellite which wanted to see if there are differences in the temperature. Because if the universe was nearly homogeneous, I mean if it was absolutely homogeneous, how can you have large-scale structures? How can you have galaxies? How Darren Crowton could have given the first 2 lectures if there were no perturbations, right? So there was an issue. So until the 90s, there was a problem. Like people thought the universe was too homogeneous to give rise to the structures we see today. And there was a satellite named COBE that started measuring the temperature differences. So what COBE saw was first very homogeneous cosmic background radiation. When you subtract the homogeneous thing, you see our galaxy in the middle, and you see difference in temperature. What are these differences in temperature? These differences are our motion against this mean CMB. So it's just the Doppler shift. We have our peculiar motions in our galaxy with respect to this radiation, and we see this. So we can measure the difference in temperature, and this is the speed of our galaxy with respect to this reference frame of the CMB, which is sort of a peculiar motion, okay, normal peculiar motion. So this is what when you take out the homogeneous part. So now let's take out the dipole too. But first, sorry, let's recompile what we learned until now. We were discussing the homogeneous universe, and we started here at the formation of light elements. So we started at the primordial nucleosynthesis, And of course, in between, here the universe was dominated by photons, as I said, was radiation dominated. When the universe becomes, recombines, which gives rise to the CMB, the universe is already matter dominated. So here it's expanding because of the photons. Here the number of photons decayed by the expansion, and the universe in between becomes matter dominated. Here you have the recombination. After some time, when the photons decouple from the baryons, which it was a plasma, so baryons could not cluster because the photon was highly coupled. When they decouple, you can start forming structures, and this is the temperature today. If you go backwards in time, many other things happen, even with known physics and with more speculative physics, but we can discuss this during the questions. Any questions so far? Okay, we have a little time left, I mean not so little, to discuss the CMB in a bit higher detail. So as I said, there is this homogeneous part, there is a dipole, so let's get rid of this. So homogeneous, dipole, let's subtract the dipole. You see our galaxy, but you start seeing fluctuations at the level of 10 to the minus 5 in the temperature, right? So the temperature fluctuations discovered by Kobe were on the 10 to the minus 5, right? And the people that made these observations, both the high precision measurement of the black body spectrum and the precision measurement of the anisotropies, they also got the Nobel Prize. So Nobel Prize for discovering the CMB, and Nobel Prize for discovering the anisotropies and precisely measuring the black body radiation. So if we subtract the galaxy, and if we look at higher angular precision, like with the doubly mapped satellite, what we see is something like that. So this is just our sphere, right, open in coordinates. So this is just a shell, spherical shell, which represents the last scattering surface. The last scattering surfaces is what we saw in the beginning. Okay, this is we call the last scattering surface, because light is being scattered all the time, and here's the so-called last scattering. Of course, it can be scattered from here to here, but this is the last scattering by the initial plasma, the primordial plasma. So we call this last scattering surface, and it's a very thin shell, right? This is a very rapid process, and this happens at redshift 1080 something. Okay, so this is the last scattering surface, and now we make a plot of it, only focusing on the temperature differences. So here's one temperature, here's another. Okay, that's a nice map, but if I want to extract information from it, I have to do statistics. That's why cosmologists all the time are doing statistics. You do statistics of large-scale structures, a statistic of the temperature fluctuations. So here what you do is you compute the product of these two temperatures as a function of angular scales. So a mean of a product gives you a power spectrum. And you can expand this, so this will be a function, and you can expand this in spherical harmonics. And if the universe is really isotropic, you can make the mean over all the m's and get the CL. So let's go back. So we compute the correlation between temperatures as a function of the angles, right? You expand this in spherical harmonics, so the components of this spherical harmonics expansion are the ALM. So they encode the amplitude of the fluctuations as a function of scale. And then you make a mean for all m's, and you get one single quantity that depends on L. So L is like when you make a Fourier expansion, and K is the inverse size. L is like the inverse angle. So it's connected to the angle, but is in a harmonic space, right? So this is the quantity that will make a lot of plots. We call the correlation function. Any quantities, sorry, questions so far? The quantities, we'll see them. Okay, so now we have this thing, and we'll show a more recent plot by the Planck collaboration. So you see an enormous level of details. You're looking at really small scales, L of 7,000. Okay, so if we want to understand, these fluctuations, because really now we are at the point where we may not know the origin of these fluctuations, and I will not discuss in this course what was the origin. Let's take this as an initial condition now, right? But we are at a point that if we understand very well these are the initial conditions for the onset of large-scale structure formation and the onset of galaxy formation. So it's really this picture that gives us the transition to understand the first part of the course. If I want to study this, to understand this, what goes after this and what went before, so if I want to understand how does the perturbation got this shape, and I want to see how they will evolve in the past, I have to do perturbation theory. Of course, as I said, we have to use general relativity. So this is a general relativistic perturbation theory, and you have baryons interacting with photons, so you have Boltzmann equations. So what really has to be done to understand this is to study a set of relativistic coupled Boltzmann equations involving all these fluids that are involved in these physical processes, right? This, I cannot put these equations in a screen, but people solve this numerically. They are public codes. They're very high precision, independent codes doing the same calculations. They all agree. So it's sort of complicated math, but can be handled. But just to give a little hint, what we have to do, instead of getting the metric of the homogeneous and isotropic universe like I did before, my former metric was this G0. You have to study perturbations, right? And these perturbations are, this is a 4 times 4 tensor, so there are a lot of degrees of freedom. So we can study how these degrees of freedom evolve in time, and that will give you how the perturbation do. I will not discuss this, but we can discuss this in the questions. The point is that for fluctuations in the linear level, there are two fields that are important, and these two fields are which will produce everything we know on the CMB, basically, right? So if we know how these fields evolve, we know how the perturbations on the CMB will evolve. Any question? Okay, so there's one point also, and you can, those that don't speak Portuguese can learn here. There's one important point is that these small fluctuations that you measure on the CMB, if there was only baryonic matter, they could not evolve into the large-scale structure that we see today. Why? Because there was not enough time for these small perturbations to grow until the large-scale structure. So what happens? What happens is that, remember that I told yesterday that when the universe expands fast and it's radiation dominated, the fluctuations cannot grow. Okay, so in a radiation universe, in a radiation dominated universe, no matter what was the initial conditions, the amplitude of fluctuations will not change. Now, when the universe becomes matter dominated, just because the matter density decays less rapidly than the radiation, so when the universe becomes matter dominated, and this happens before decoupling, then the perturbations can start to grow. So matter can start to condensate. Which matter? Only the dark matter. Why? Because the baryons are coupled to the photons. Okay, so way before the CMB, the dark matter can start to clump and evolve, but the photons can, but the baryons cannot. After decoupling, then the baryons can grow. The amplitude of the baryon perturbation can grow. And what happens, it goes to the potential wells that were produced by dark matter. So the dark matter triggers the star formation because it can clump before the CMB. So you really need to have dark matter also to be able to explain the large-scale structures today. Okay, so I told you that if you want to get information from the CMB, you have to compute statistical things. One thing is the power spectrum, but anything you compute, you do statistics, and you need to understand that equation that I mentioned before. So we would translate the physics of this, say, early universe at decoupling to things that we measure, like the temperature differences. So you have a photon there. There is the last scattering surface. There is a photon here. What will happen to this photon? If there is a potential well, this photon will have to get out of the potential well, so it will lose energy, right? So you see there is phi is negative because it's a well, a potential well, so phi is negative. So the photon will lose energy when it goes out of the well, and this will produce a temperature difference, right? Also, there is a Doppler shift, that if the photon is going in our direction, and these are points outwards, but if the photon is coming inwards, right, we will see a blue shift, so you see an increase in temperature. If it's going outwards in the same direction as R, it will have a red shift, right? And finally, so this is a gravitational redshift, this is a Doppler redshift, and if the photon is in a denser region, it will be hotter, just because, gas compressed gets higher temperature. So if there is a positive density perturbation, so this is how more dense this region is with respect to the mean. If it has a positive density perturbation, it will also produce a positive temperature fluctuation. So when you look at the anisotropy maps, which are the difference in the temperature, what you're measuring is a combination of these effects, a gravitational redshift, a Doppler redshift, and an intrinsic temperature difference. But all these quantities, they depend differently on scale. So when I make this plot as a function of scale, I'll be probing all these things. Okay, so this is what I just said, and for very large scales, these two things combine into one, and I expect like a flat, dependence. But what affects the CMB temperature is not only what happens when the photon decouples here, but also what happens along its propagation, right? So if I have a galaxy cluster here, for example, or a big dark matter perturbation, the photon gets in and then goes out. It gains energy and loses energy. And if this potential is static, the energy that the photon loses is the same, the gains is the same that it loses. So it is not, no change. But if this fluctuation is evolving in time, and in our universe it is, if it's big enough, the photon will get in when the potential well is smaller, and will get out when the potential well is larger. So if the potential well changes in time, I will be able to measure a difference. And this is very important because in a universe without cosmological constant and dark energy, the potential wells in the potential, they are constant. Although the matter grows, so the density varies, but the potential is constant. You can show that. So the potential only changes if there is dark energy. So this secondary anisotropy, we call it because it's produced by matter in between, is also a measurement of dark energy. And we call this integrated Sass-Wolff effect. Okay. So all these quantities, the integrated Sass-Wolff effect, and all these primary anisotropies, they have different scalings with different reasons. But let me just jump to a power spectrum. And this is the outcome. So what you see is the amplitude fluctuations are a function of angular scale. They have a large peak, and they have these oscillations, right? This peak is connected to what we call acoustic oscillations. You have this fluid which has photons and which has photons and baryons coupled, and this thing oscillates. For very large distances, there is no time for the pressure to take action. So in very large distances, nothing happens. But if in a small distance, if I compress this thing, it will oscillate, right? So the Jeans thing. So if you are at very high distances, there is basically you compress and the thing will be compressed. But for distances which are less than what we call acoustic horizon, so where the propagation information can communicate, so for regions smaller than this acoustic horizon, you have oscillations, and for larger, don't. So this is the first peak. All these peaks are connected to this oscillation. It's like when you have a peak in real space, when you go to harmonic space, that produces other peaks. But these other peaks are affected by many things. So let's see. First, and what I think is really absolutely fantastic, this picture was not produced in early times by trying to explain some data, by trying to fit some data. This picture was produced by having a model and studying the consequence of this model. So if you have a cosmological model that has these very early times and where you have nucleosynthesis, when you have a couple photon baryon fluid and so on, if you follow this thermal history of the universe, if you have primordial fluctuations, which people expected to be scale invariant because of theoretical reasons, this is what comes out. So you predicted this is this very detailed shape from a model way before there was data. And it turns out that the model fits the data. So of course the model has free parameters. This plot in this case has only 6 free parameters. But what I find absolutely amazing is that there was a clear prediction. So you're not explaining something that happened, but you are checking a prediction that your model did. And that's, for the history of science, it's very different, right? It's not the same explaining something a posteriori than predicting something. A theory has to have a predictive power. And if you do this, that gives a lot of credibility to the theory. That's why when there is a disaster, like a natural disaster, afterwards, there are lots of how you say vidente in English? I don't know, people that predict the future. So after there is a disaster, there are lots of people that have predicted the disaster. But you only know afterwards. So it's very easy to predict the past. What's different is to predict the future, right? So that was like a real prediction. I won't go into the math, but one important thing is that this distance here that I said is connected to acoustic oscillation provides also a standard distance scale. We saw supernovae is luminosity distance, so it's a standard candle. This first peak here is what we call a standard ruler. So we know how to get it as a function of the cosmological parameters in a very clean and neat way. So this is the expression we call the angular diameter distance, and this is connected to the photon baryon fluid. It doesn't matter the details. The fact is that if the universe has gone through this thermal decoupling process, and there is these fluctuations, I have a standard ruler given by this first peak. And if I have a standard ruler, I can constrain these parameters, remember? So a prediction is that if the universe is flat, for example, this L should be around a degree scale, which is exactly what you see. So when you see this in the degree scale, this already tells, look, the universe must be at least nearly flat. The amplitude of the peak depends on the ratio between the omega baryons and omega matter. If you increase omega baryons, the peak goes up because it's the baryonic process of this photon baryon fluid, right, oscillating. It's pressure. So it's a baryonic process. More baryons, the peak goes up. But the more dark matter, the peak goes down. It's the first peak here. But the second peak is different because if you increase the baryons, the second peak goes down, and with the omega matter, it goes up. So it's a different behavior. So if I see two peaks, I can already disentangle and measure omega baryon separately from omega matter. And this position tells you the universe is almost flat, as I said. Here, if the universe is flat, which means the omega k is 0, and omega matter is 0.3, we know this for many, many reasons, but 1 minus 3, you need something else. So it's a completely independent indication of the presence of dark energy. And as I said, you know, the difference between the first and the second peaks tells you about dark matter without any of the other observations that I mentioned before about dark matter. Forget virial motions, forget galaxy rotation curves, forget bulk motions, forget everything. It already tells you you must have some dark matter, period. Forget about Big Bang nucleosynthesis. And the difference between these two peaks, the peak and the valley, tells you how much ordinary matter there is. Forget Big Bang nucleosynthesis. This alone gives you a measurement of omega baryons. And as I said, gives you alone a measurement of the flatness, which gives you an indication that something has to build up 70% of the energy density of the universe. So this is really impressive, and that's why I'm not speaking about my work, which I think it's great, of course, I'm doing that work, but I think that CMB is so important for cosmology that I'm skipping everything I do just to give attention to this. So this is a more recent plot by the Planck collaboration, and you see you go down to very, very high distances. Here you have a lot of this cosmological information, and we'll see what's encoded in here. So, okay, still have a few minutes. So we discussed the primordial anisotropies, right, which happen in the last scattering surface, and also this integrated SAS-Wolf. But in between, there's also gravitational lensing. There is also this Risch-Sciama effects, which is like the integrated SAS-Wolf, but produced by structures in more recent times. And there is effects Sunyaev-Zeldovich, there is gravitational waves. So everything that goes between the last scattering surface and us can leave an imprint in the power spectrum. This is the total power spectrum, and this is the component. So you see, for example, that at very small distances, very large L, very short distance, as I mentioned yesterday, your amplitude that should go to 0 is not 0 because of gravitational lensing, right? So you can start measuring the weak lensing of the CMB background. And this is another effect that is not shown here is the Sunyaev-Zeldovich. So you have the galaxy cluster here. So it has this very hot gas, not dense, but very hot. CMB radiation here. So the photon interacts with the electrons, and it gains kinetic energy. So the presence of the cluster here will disturb the CMB background. Of course, this is in small scales because it's the angular scales of the clusters, but it will leave an imprint that if you look at the maps, so here is the CMB in blue, so it has very small fluctuations in small scales. It's almost homogeneous in small scales, but then you see something suddenly appearing, disturbing this background. These are the galaxy clusters, right? So you can detect galaxy clusters not by the galaxies, but by the effect that the hot gas makes on the CMB background. This is just one example, space SPT South Pole telescope. So here are 3 clusters, and what's interesting is that this effect on the CMB, this perturbation on the CMB, does not depend on the distances. You know, I told about the supernova, its luminosity distance. The further the supernova will be, the fainter it will be, right? If I want to detect the X-ray of a galaxy cluster, the furthest the galaxy cluster is, the less X-ray I will receive. But this perturbation on the CMB is not connected to distance. So I can see even very distant clusters. So here is the distortion on the CMB of clusters that are at 0.7 redshift. So I can see very clearly the X-ray emission. A redshift at 0.5, it's already dimmer. And a redshift at 0.83, I almost don't see any X-ray, but the Suniav-Zeldovich signal is pretty constant. So I can detect clusters at a very high redshift, and that's one of the powers. But the CMB is also polarized. I was discussing temperature differences, but there is also polarization of the CMB. So you can see directions of all this temperature anisotropies, and this you can compute also the power spectrum of this polarization, and it contains a lot of information. So for example, here is the power spectrum of the temperature that I shown before. If you measure a polarization, you have a polarization map. So it's a vector, how you say, a map of little vectors, right? So we always, when you have maps of little vectors, we compute the divergence-free part and the part that's a pure rotational, right? We compute the E modes and the B modes in a very similar way to the electromagnetic field. So you have this field. You have one part that's purely a divergence of some vector that we call electric in analogy, right? We call E modes. And there is a part that's purely originating from the rotation of a vector. So there is a Helmholtz theorem that tells you that any vector field can be decomposed in 2 parts. One purely rotational, one pure divergent. So you only do this. There is no physics involved, right? It's just math. That's a vector field, Helmholtz theorem, and you decompose. But there is physics in this difference. That's why you do, of course. So you have the E modes, the B modes, and you can, for example, compute the correlation between the E modes of the CMB, and it gives another curve here, like the red, which has, of course, an amplitude much smaller than the temperature. And you have also the B modes here. So it's much harder to detect, it's more recent detection, but they have other information. For example, gravitational waves, they produce B modes. So if you measure just the B modes, you can measure gravitational waves. So this is a polarization map, more recent, from the Planck. And all these curves are the directions of the little vectors. So you can compute the EE power spectrum, for example. So it's the correlation of the E modes in each point. You can compute the TE correlation, so correlation between the E mode polarization and the temperature. And you have these plots. And the red curves are always fits to the data. But again, it's quite amazing that a single set of parameters fits well the TT data, the EE data, the TE data, which are independent. Okay. I have 2 minutes, but I would leave you without questions, right? So let's not use that 2 minutes and just say that, just to recap, that these small fluctuations in temperature to the 10 to the minus 5 that are on the CMB, these are the fluctuations that are evolved into large-scale structure, first linearly because are small amplitude, and then non-linear to produce the large-scale structure and go down to producing the galaxies. Of course, when you go to the non-linear part, you have to run very large and complex simulations, which sometimes are only n-body. And to produce galaxies, you have to paint there using some criteria, and that's where semi-analytic modeling jumps in. Or you can try to do with more physical processes during hydrodynamical simulations. But even the more complex hydrodynamic simulations then cannot have all the physics down to very small scales to produce galaxies. So in any case, we are not yet at the point of going from the very early universe at inflation to a final galaxy, but we are incredibly close to that. That's pretty amazing, right? It's incredible that you can have something like everything, the universe, and maybe we think we understand it with a very few assumptions and very few parameters. So okay, so that's small fluctuations in temperature, which are connected to small fluctuations in density. And besides this, you know, there are the fluctuations of the dark matter, and the fluctuations in the dark matter produces potential wells, which amplify these fluctuations in the baryons, which then evolves to the large-scale structure. So I skip all this and just go to the conclusions. Oh, I thought I had, this shouldn't, okay, so good. So in these 2 lectures, okay, there were 2, so I focused in 2 observables that we could, one that we could work out in a lot of detail, the type 1a supernovae. So we could really go down to a model and compute the observable as an integral, so really very easily. Of course, all the complexity, as I say, is always in the systematics. So there's a lot of works, not to understand the integral, but to really be able to calibrate the cosmological distances. Then we look at another observable, which we looked into some detail, which is the CMB, that I have called this holy grail of cosmology, because it contains so much cosmological perturbations. It's so clean to produce because all equations are linear. It was predicted before the observations, and it provides the seeds for the large-scale structure that we see today. But of course, cosmology has lots of data. I didn't speak a word of large-scale structure. I didn't say a word about galaxy cluster. I didn't say a word about weak lensing. And these are 4 of the main cosmological observables nowadays. Lots of data with high quality. I mean, high photometric quality, high image quality, deep, etc. And that's a lot more to come. Of course, cosmology is a very interdisciplinary field. When I started the field, I'm a bit old, but I'm not that old. But for many people, cosmology was just doing general relativity. No, it cannot be more false than that, right? Of course, it's good to know the general relativity, but if you just know general relativity, you don't know anything of cosmology. So really interdisciplinary field. And it involves, of course, a lot of astrophysics, and that's why I'm here. But it's a very interesting field where you have this interplay between the astrophysics and fundamental physics, right? The questions we are asking about dark energy, about dark matter, and about the early universe, they are not just like complex applications of known physics. They point us to the unknown physics, to the very fundamental physics at the very fundamental level. We are speaking about the fundamental Lagrangian of particle theories. That's what we can probe with cosmology. And cosmology, in a way, has taken the lead from accelerator physics in the sense that we know that there is physics measured beyond the standard model of particle physics, and now the particle physics has to explain. Up to now, the physicists know that the standard model is incomplete due to some theoretical reasons, but what they measure at most was the Higgs, which is still part of the standard model. So it's really incredible that by looking at the universe, first, we think we understand many things, and we are pointing towards new physics. Of course, all this can be wrong, right? But it's amazing. So we have an incredibly successful model, you know, to be able to reproduce the CMB, large-scale structure, nucleosynthesis, and many other observables with a few simple physics is quite amazing. But of course, there are many, many open problems. We don't have time to show them. One, I was going to add a plot. I forgot a question that Claudia asked yesterday, that you have independent ways of measuring the Hubble rate. And with CMB, you get one value. And with other observables, you get a different value. But now the error bars are so small that they are conflicting in many sigma. What's the region? Is there something deep? Is there just a problem with cleaning up your CMB maps? Or is there something deep? So there are many open problems. Not only the nature of dark energy and dark matter, but some people argue that you find preferred directions in the universe. There are the small-scale problems in the dwarf galaxies and substructure in general. They may point you to new matter, but it can be something deeper, more different. So we, of course, have to be open. I try to be conservative, and I explained why. I think it's because of our idiosyncrasy. We need to be, in a way, conservative, but of course, we have to keep an open mind, and we know there are open problems. So it's quite of exciting times, because you have success, you have data, and you have problems that you have to solve. So the word is yours. I mean, those that want to do cosmology, they have a lot of things to do. You have a lot of things to play with. But please be careful. But I'm saying that because you have to understand the data, right? You have to understand the data. This is very important. You cannot just get a table of numbers and fit this table and say that I'm constraining my model. I saw people, for example, taking data from the supernovae that they are produced for a lambda CDM universe. They do it in a very correct and smart way, but which is only valid from a lambda CDM universe. And they pretend they obtain constraints in different models. It's wrong. You cannot do that way. You have to understand how to do this data analysis. I see people taking error bars of power spectrum and computing just like if there were error bars. But in reality, this data that they take is correlated. You need a covariance matrix. The error bar is just to illustrate some idea of the error bar because they are inverse of the diagonal terms. Only that. So you have to go, be careful, please. And also, precision cosmology, which we are reaching now, so error bars are getting small, it means exactly that the systematics error bars are dominating the statistics. I was hearing how it's called, I forgot. I was hearing this for a decade, and now it's the truth. So you really have to take care of systematics, and most of this is astrophysics. So you cannot do cosmology without knowing astrophysics, right? So astrophysics is absolutely fundamental now. Sorry?
You should come and tell my colleague.
All right, okay. So you cannot say, you know, I do cosmology, I don't care about galaxy evolution. It's not a choice. You cannot do that, right? And of course the converse is true, like I said yesterday. You cannot say, I'm interested in galaxy evolution, I don't care about the universe. Wait, but these galaxies were produced in the evolution of the universe. So really astrophysics and cosmology are very intertwined, and that's exciting, I think. But it makes life difficult, which is interesting too. Another thing is, please avoid confirmation bias, right? So I won't name my student, but once I was doing analysis with a student, and he said, look, but W is much smaller than -1, so we shouldn't report this. I said, no, you can't do that. You cannot refine your analysis until you find something that matches what you expect, because then you miss everything, right? So it's very hard, because everything points to something, and you want your data to point to the same place that everybody's pointing. But if you do this, and of course you don't do this intentionally, but it's easy to get fooled by that, you are doing bad physics, right? So it's very hard to avoid confirmation bias, because when you find something weird, you refine until you find something that's not weird, but not weird compared to what you expect. So it's a bias, right? So if you can do the analysis in a, if you can do the analysis in a blind way, and lots of surveys that have lots of people and can think about it, try to do it now. You set a data analysis, but you make something to the data that nobody knows. So you should not expect any number, because the data has been multiplied by a factor that you don't know. So you make the data analysis as good as you can, and when you're very confident that this data analysis is correct, then you unblind. You may find what you don't know, what you don't want, but at least it's the best you could do, right? And also, relax and have some fun, right? This is all very fun, very enjoyable, right? And sometimes when our everyday life makes our life tough, you know, for everyone, and competition, and fellowships, and money, etc. But let's try to relax and have some fun. Thanks.
So, thank you, Martin. Do we have any questions from the audience?
Sorry for taking a bit of time.
Regarding dark energy candidates, can you talk a little bit about how dark matter and dark energy can be related?
Right, so the way we thought with this quintessence thing that we named for funny reasons is that where we measure dark matter is where there is higher densities of matter, right? So where we see clumping is where we detect dark matter. And when we see dark energy, only very large scales. So what we thought is, let's think about some equation of states that when the density is high, the pressure just goes to 0. And when the density is low, the pressure gets negative. So we thought about something really simple. Just think about this. P equal minus A over rho to some power. So, okay, when the density is high, pressure goes to 0. When the density is low, you can show and that a dynamical process shows that this is a limiting case. Very, very simple. You can do it in one line. So when the universe expands, density gets low, and it's like a attractor. So this goes to this situation. So it seems very nice. So we were very excited. Later, before publishing this, we discovered that the equation of state like this, but with alpha equal 1, the people from string theory, they were studying this. It was called Chaplygin gas. So it even appeared to have some like more fundamental physics motivation. But so we started, we used supernovae and a lot of data about the homogeneous universe, and that was fitting very well. But then when you look at perturbations, it's a hell. So this thing produces a lot of perturbations that you don't see. So you can try to fix this and say, well, but these are perturbations of the matter. Just look at the dark matter, and we can tweak things a little bit, and it gets a nice spectrum. But then if you would look at the lensing, then it screws again. So, you start tweaking too much your model. So basically I said, well, it doesn't work, right? You still see a lot of works in the literature with this kind of model, etc. But basically, if you have to tune your initial conditions and tune your parameters, then the idea was to unify to make it simple. So it doesn't work. But that was the idea. But there are other ideas trying to unify also in different ways, but none of them that I know really work in the sense of making a simpler theory fit the data.
You have said that everything seems to point out to a flat universe with a slight curvature. Does it matter if it's closed or open, and how can a flat surface be closed?
Great question. So what we were discussing is geometry, so curvature is a local thing, but you may have a topology that goes in, right? So I have a very good case here that I want to make publicity, so I can use it for my topology discussion. We have arranged that, right? So this is a flat universe, just a piece of paper. If I draw triangles and circles, they will have all the Euclidean properties. But if I just make this, what happens is I can do a trajectory and I'll go back to the same place, right? So it's closing in this direction. It's an identification of the two sides. So we call this a non-trivial topology. Why topology? Because it's a global property. If I draw circles, and I shrink the circles in a simply connected universe, any circle can be shrunk to a point. But if I get this circle here, I cannot shrink it, right? So it tells you there is a topological difference. And I can identify one side with this, I can identify this with the other, I can make a torus, and I can make a lot of non-trivial topologies in the way I want, and they don't depend on the size. So I could have a very small universe, which looks like our universe. So what impacts does this have, you asked, right? So one impact is that I would start seeing a replication of images, because I can, I'm observing, I'm here, let's do this. I'm at a point here, I'm observing an object here, so light goes through here, but it can go through this direction too, right? So I could see maybe two same objects in two different directions. So there are all kinds of strange things that happen when you put non-trivial topology, but basically you see repetition of patterns, and you could see this in the CMB. So a lot of people put a lot of energy trying to see these patterns with many different topologies, but nowadays I think no one really talks about that anymore, because we didn't find any of these signs of non-trivial topology. So if we are in a universe which has non-trivial topology, but if the last scattering surface it's smaller than the size, so if the last scattering surface is a circle like this, I will not be able to probe the rest. So with light, I think we are down to the limit where we cannot probe non-simply connected universes. Although it's very complicated because the pattern don't repeat, because as I showed, there are many contributions to the SMB, but people has looked at this into a lot of detail. So even when you consider all the complexity, no sign of a closed universe was found. Perhaps if we detect primordial gravitational waves, which come from way greater distances, we will be able to constrain this to larger. But basically, if the universe is large enough, maybe we'll never be able to tell if it's not simply connected.
My question is about something that you do not really mention. The point is that supernovae are so good as probes for cosmology, And there are people like me and that we wonder, we're worried about the fact that you don't know how they're forming. And if there is any, or if you guys during cosmology think about the impact that the different ways of forming a supernovae would have in cosmology.
Right, so that's a good question. So all this is empirical, right? No real simulation with all the physics produces this. So you think you understand because these are maybe white dwarfs that are close to a critical mass. So there's hand-waving arguments, but really there's not a deep quantitative knowledge that the supernovas are really standard candles. So people do go in two different directions. People that are really interested in supernova, they try to see a supernova in different regions of the galaxy. For example, if you're close to the core or less, if they depend on metallicity, different kinds of galaxies. So they do all kind of, again, empirical, but more detailed studies to see if they find some dependence on the ambient, and many quantities. Others that try to focus more on the physics of supernova itself. And others say, well, okay, supernova, it's one probe, let's look at different probes. So I didn't tell this, but since you asked, gravitational lensing provides a way to measure the Hubble expansion, which is totally independent of supernova. I won't show that, but I bring a gravitational lens, so you can enjoy. My point is, if you look at the gravitational wave, at the gravitational lens, let's see if this works. Okay. Oh. I need some light source, so I'll ask Thiago to keep a laser there later. So you see the laser you see with the lens. Okay. Sorry for taking long to answer the question, but this is funny, so. I can be there.
Aqui tem um laser.
So use the laser because just to have a reference, not to mix up. You see two images of this laser. If you align very well, you'll see a ring, which is the Einstein ring. And if you tilt a little bit, you see more images. You'll see 4 images. So you can see this phenomenologically. I'll pass this on. So the gravitation, this is really the light deflection, the same mathematical light deflection that a gravitational lens produces, right? A model that's widely used for galaxies, stimuli isothermosphere. So this is a good representation of what happens in practice. And you'll see several images, so I can pass this on. But what's the point? Is that these different images, sorry? Bota ali assim num lugar meio isolado, tipo aí. So these different images, if the source is varying in time, for example, is a QSO, variable QSO, you see a different variation in time of the different images, right? Sorry. You put the laser there, and you see through the lens. The laser will go straight to the right. So this laser simulates our light source, and you look at there. Yes. Okay, so let me show again. Okay, you really use as a lens, so you look through it, and you see 2 images, you see arcs, or you see a ring, and if you tilt, you see more images. So look through the lens. But you can pass this, you don't need to move, you can pass the lens, right? We keep the laser, and you pass the lens. So, right. But why I'm showing that? Because if the source is varying in time, the different images will have a different time variation. So there is a time shift between the different images of the lens, right? And with this time shift, you can measure H naught totally independent from the distance ladder at all. I mean, it doesn't depend on C-feeds, doesn't depend on supernova, anything. And you find, and there's a plot I will show, you find the agreement with the supernova, not with CMB, but with the supernova. So it's very independent. So we are confident about the supernova results, not because empirical calibration supernova, but because independent, distance indicators that give the same results. Yeah.
And I need to keep holding this steady. I'll try not to move it too much. It's still following what Denise has said, and this is something that I was talking with Rafael as well yesterday. I think if we take, and this is a comment, this is the way I understand it, though, if we take the supernova result by itself, then it's not very robust. It's true. Thank you. So it's actually quite robust, but it's one result. But if we combine it with the CMB, the results on the plane on omega matter and omega lambda are orthogonal, and they fall in the same place. But to me, the main thing is something I like to show the students. I don't know if you have that plot there. There's a third measurement of omega matter, which is completely independent, and that's the galaxy cluster measurement, which falls exactly on the same place. It's highly independent of omega lambda, but the supernova and CMB combined predict omega matter very close to 0.3, and the clustering of galaxies shows that this is exactly the result. So it's true that the supernovae, we don't understand. We think they're binaries with the white dwarf, and that works quite well. But if you combine all of the cosmology results together, it works amazingly well. And this is, I think, what he was showing in the last slide. And for me, that's what really convinces me that we're on a good track with cosmology, with the standard cosmological model. I don't know if you agree with that.
Yeah, fully agree. More questions? So sorry, just to comment about this. So in red, the supernovae measurements of the expansion rate. In I don't know, cyan, they are totally independent measurements, like Lansing, Sunyaev-Zodovich, Mazes, etc. But they have large error bars. And there is the CMB, very small error bar, very far away. So people try to ways of finding agreement. Maybe you need to have a bit more of curvature, more neutrinos, like an additional species of neutrino, or a different W, and they try to, so it's an open problem, where it's a simple solution or deeper.
So we're, huh?
Alan Sandage, before passing away, wrote this paper in which his H naught was 62, and it was based on metallicity correction of the Cepheids, which you then build up the distance scale. I found disturbingly close to the CMB, because those are really independent, and yet far away from this bunch here.
Right.
You have, and then he died, so we don't know yet, unfortunately.
Yeah. Definitely something that has to be looked at. We cannot overlook this. So
we have one last question because we're approaching 1 o'clock already. So this is the final question of the school.
So again, about the curvature of space-time here.
yes.
I do not understand very well how do we measure that curvature experimentally.
Right. So I didn't show this in detail, right? But if you make the plots, you see that, let's see, yeah, maybe this. If you make the plots, you see that the first peak provides an absolute distance scale, which is connected to this RS. There is what we call the sound horizon. So it's a physical distance that you know, and this is like a standard ruler. We have standard candles, standard ruler. So we know the physical size, so we can compute the angular diameter distance by this position of the first peak. But if you look at this equation, this integral, right? And now the way I put here, this S is a function of K. So this S can be a sinus, a hyperbolic sinus. So it depends on what you put there. So you can show that this position of the peak is very sensitive to this difference here, right? So this difference is exactly the curvature. So if you make the plots, you'll see that the most of the sensitivity of the position of the peak is given by this, right? Not this part. And so it just shows you that the first peak is very sensitive to the curvature. I don't know something more intuitive to say, but that just happens to be the dependence. So by measuring the position, you measure the curvature. So I know I passed away time, but I asked if I could do some advertisement, and as I have the microphone, I can use this privilege and make the advertisement, right? So I'm trying to go very fast. It's just that next year, so we have a lot of time to plan, there will be a workshop, and this workshop will be in São Paulo because they have money. We don't. That's a problem. So this workshop will be in São Paulo. But it's a workshop on dark matter and neutrino detection, right? So why do you care? These are 2 weeks. So the idea is to provide a theoretical overview. Can I use the laser just a second? So you see neutrinos in cosmology here. You see dark matter, of course, everywhere. You see small scale problems, which are totally from astrophysics. So there is this to provide a background for astrophysicists, for particle physicists, on the problems connecting dark matter and neutrinos. So if everyone is interested, this will be really basic to start with. So it's a theory week with practical activities like exercises, coding. And then the week after is connected to detectors. So the techniques and the apparatus and the detectors that try to detect dark matter and neutrinos. So if you are interested in these subjects, just keep your eye that will open registration at some point. Earlier thing that will happen this July, not that next year, is the Brazilian School of Cosmology and Gravitation. So I'm making publicity because it's at CBPF here in Rio. It's my institution. And then, of course, it's a cosmology, 2-week cosmology school. We have courses on gravitational waves, on perturbations, on early universe, and on dark matter, lensing. So if you're interested, registration is still open. Here it is, the website. You can go and pay your registration, or you can even apply to waive registration. And finally, of course, if you like Brazilian music, and of course, if you think we should vote for president and not let this corrupted Congress decide after 10 years goes down, that we know he will. So there is a show, so you can do 2 things. You can protest and hear very good music on Sunday. Please double check, because, you know, double check times, double check everything. But this will be, I think, a great, great concert, and also a way of doing some manifestation. So thank you very much.
This was really nice.
We want, all the teachers, thanks a lot for the organization of this extremely nice school. And we want to give some flowers to those people that had organized these things, to Lori, to Karen, and to Denise. For me, it's easier to give presents to ladies, but I want to I want also to thank a lot all the other people who helped. Some of them we don't even know the name, but I think